welcome everyone to the ASIAA program today. So we are happy to have David to continue his series of 2 talks on DESI and its future. So today is about a brief review of DESI results and the grand plans David has in mind for DESI 2 and future spectroscopic projects. We can call him the king of specs. For those of you who didn't go to the joint colloquium yesterday, let me briefly recast David's career. So in 1995, when he was about to graduate from Berkeley, his advisor, Mark Davis, suggested that them to construct the extinction map of the Milky Way, and they agreed, thinking this may just take a summer. And since David was leaving, they recruited another graduate student of Mark's, Doug Energy. And 2.5 years later, they finally finished that 1 summer project. And the result is this SFE 98 paper. For optical astronomers, I bet you already have used the extension derived from SFD a million times. So you owe this to this gentleman. So after SSD 98, you can see over there. That's my seat. David went to Princeton to help set up the spectroscopic pipeline. And since 2004, he returned to Berkeley, joined the Berkeley lab as a senior scientist. And he became the PI of the BOSS survey, which was the 3rd incarnation of Sloan. And since 2013, he has been the project scientist of DESI, which is this incredibly successful redshift survey that we'll hear about again. So let's welcome the king of specs.
Okay, who is looking for a summer project? I have some great ideas. Okay, so I'm going to tell you about the first results from DESI, which just came out on April 4th of this year, so very recent. And then plans for what we're going to be doing with DESI and plans for what we'll be doing into the 2030s. And let me start by just thanking this project is primarily funded by the US Department of Energy, 2 private foundations, and now we have 72 participating institutions, which is phenomenal to see. When we started this project, it was, as all these big projects are, you start small and then you look around, before you know it, you have 800 people. Okay, so what is this project, DESI? So as you might guess in the name, it's designed to study dark energy. And to do this, we've constructed first the largest 2-dimensional map of the universe. I'll show you that briefly. And so this will actually be the largest nearly full sky map of the sky prior to LSST Rubin Observatory later this decade. We've created what right now is the largest 3-dimensional map of the universe. And this is to study the history of the expansion of the universe. And I think you're all astronomers, right? I don't need to talk about this, right? I just need to show this is what we're measuring, is from the epoch of deceleration. And what I'd like to just point out here is there's very little data as far as what's happening in the decelerating epoch of the universe. So most of the data that we have in terms of dark energy is in the later times when the universe is accelerating. Okay, one way that I like to think of these questions is, these are unexplained forces of nature. There are several of them, and is this one force or two forces or more than two forces or fields, depending on how you look at it. And I don't know if this phrase has any meaning here, but whether the tooth fairy has come one or more times. This is just where you say, I don't understand what's going on. I have to make something up. And so the two terms that we've made up, of course, are dark energy, which is pushing the universe apart today. And in the very early universe, there was inflation, which was also a period of accelerated expansion that then turned off at just a fraction of a second. Okay, how do we measure the expansion history of the universe? The two general kind of approaches are to have objects where you can measure their distances object by object. And so this is how dark energy was discovered 25 years ago, using supernovae as your standard candles of how bright you know they are. And then there are more statistical measures, which is what I'll be talking about, which is to use features in galaxy maps or any of these maps, including the CMB, to measure features as a function of redshift. Okay, and the feature that we're using is the BAO scale, so the baryon acoustic scale. And so this is famously what's seen in a map of the microwave background. So this is, I can't remember if this is a W map or a Planck map, but this is a map when the universe became transparent. And the features that your eye picks out here, these are the sound waves imprinted in the universe at that time. And then those overdensities have survived until today because they're large enough. They haven't been erased by gravity. And those are features that we can see in the galaxy maps today. Oops, sorry. Oh, all right. Okay, and then if you look at the correlation function or power spectrum of either of these maps, so that's essentially the first peak in the CMB maps is the acoustic scale there. And if you make a correlation function of galaxies as well, there's an overdensity preferentially at the scale of 150 megaparsecs by a few percent, which is the same acoustic scale imprinted on galaxy maps. Okay, so that's what we're looking for. These are measurements prior to DESI starting. So this is actually from the BOSS survey here. Okay, and then inflation, you can ask what we know about inflation. We do know some things about inflation. Most of the measurements are upper limits of sorts. So the fact that the universe appears spatially flat, we haven't detected, at least most people think we haven't detected non-Gaussianity in these maps. And then these primordial fluctuations they're growing mode fluctuations. But we have actually measured something definitively about the inflationary epoch, which is, this is a plot of this axis here is the primordial tilt, so the power spectrum of those initial condition fluctuations versus, this is the tensor to scalar ratio, this is the gravity waves imprinted on the CMB. And there's a very confusing plot here, but all I want to point out here is we've definitively measured that these early universe fluctuations are not scale-free by many, many sigma. And there are all sorts of different models of inflation, and I invite you to ask your colleagues about those models, not me. But if you look at all these models, there are certain of these models that are actually already ruled out just from these measurements here. And so I think some of the interesting things that are ruled out are just the simplest models of slow roll inflation actually don't fit the data already. Okay, so let me get back to redshift surveys and galaxy maps. So this is an incredible decade to be living in. So for those of you who are students, when I was a student, cosmology, not much was happening, okay? And that's why I worked on dust, because, I don't know, like, we didn't have any other good data, we'll look at dust. Today, like if you're working in cosmology, it's like, it's not always like this. It's, we just have this array of huge projects coming online in the next couple of years. So this is going to be transformative for cosmology. So these are all of the projects just starting this year and the next couple of years, making large three-dimensional maps of the universe. We're all kind of racing each other of like, who's going to be first? Who's going to start first? All right, well, it turns out this is the one that actually got on Sky first, the one I'm going to talk about. This is the DESI project. But PFS hopefully will be starting later this year. Euclid started their, they launched last year, just started their survey a couple months ago. And then these other projects are all in the next few years. Okay. For DESI, before we started, we actually needed to make a two-dimensional map from which we could select the targets that we'd be observing. We didn't have a map that was deep enough and large enough to do this. So in fact, as a side project, we put together 3 collaborations. So we did 3 coordinated surveys with, do I say here, we used, yes, here we go, 1,400 nights on 3 telescopes over 6 years. So this was actually a pretty big effort. And with this, we imaged about 40% of the sky, so most of the observable extragalactic sky from the northern hemisphere. Made these images in 3 colors. Also included infrared data from the WISE satellite. It's about a petabyte of data, and every time we wanted to reduce it, it was another 100 million CPU hours. So a big project right there. But then in the end, all we needed was, okay, here are the galaxies we're going to observe. Okay, this is one of our samples of galaxies. This figure I love because this is a map of, just a 2-dimensional map of the luminous red galaxies. And when I look at this, does this remind anyone of any other sorts of maps you've ever seen? I'll give you a little hint. I mean, it just, by eye, it looks very similar to a CMB map. But this isn't. This is really a map of galaxies selected over the whole sky. And it's a very clean map. I mean, you look at this, you can't look at this and say, oh, you must have used one set of telescopes in one part of the sky, another set in another part. It's actually a pretty homogeneous map right here.
So if you have these islands of patches?
Yeah, so the islands of patches is we took data actually only in this region here, and we took data from here on up. And then when we reduced the data, we actually took all of the available data that anyone else took from these same telescopes. So this data down here, this is the Dark Energy survey, and this goes down to near the South Pole. We don't really care about that because DESI can't point that far south. On the other hand, by including all of these data in our reductions, it actually improves the cross ties of all the calibrations of the different sets of data. So we intentionally included every bit of data that we could. I don't know who took those data, but someone did, and we put it in there. And I should say, actually, we're regenerating a new data release of these imaging data this year, where we've included all of the data since 2019 when we made this map. And that actually fills in everything except this is where the plane of the Milky Way is, but it fills everything else in. So we'll be releasing that in January.
Sorry, David, do you remember the contrast of this like color between blue and red?
I don't remember, so I don't want to say and tell you the wrong thing.
Because you compare to the CMB, right? The CMB is like 10 to the minus 5, and then.
Oh yeah, this is a much higher contrast. That's right. Yeah. And then the other interesting thing is, the Planck maps have been kind of the basis for a lot of cosmology because of the amount of information here. but this really is just a two-dimensional map, so that limits the information content here. This map is only a two-dimensional map also, but what we're doing is turning this into a three-dimensional map. Okay, so when we get to DESI, this is the telescope that we're using in Arizona. So this is the Kitt Peak Mail telescope. So we've taken this telescope and we actually, everything on the top end up here, we actually just sawed off the top end of the telescope. I don't think they used a saw, but they used something. Took off the whole top end of the telescope and we rebuilt everything up here on this telescope. So it's a telescope with a 4-meter diameter primary collecting mirror. And then we've built everything on top of this, including a large optical corrector, a focal plane with 5,000 robots with fiber optics, and then there's a fiber optic run from the top of the telescope down to a climate-controlled room down here that has 10 sets of spectrographs. So this instrument, it's designed to look at up to 5,000 galaxies at a time. Here's us starting to, actually this is disassembling what was on the top of the telescope before. And now here's us driving in the instrument. So this is the start of installation of the instrument. So this is what's called the top ring on the top of the telescope. And then it's called the barrel. Here are some of our lenses. So our optical corrector has 6 lenses. The largest one is 1.1 meters in diameter. This is currently the largest lens on any telescope in the world. And among those lenses, there's a pair of lenses that act as an atmospheric dispersion corrector. And so what this is this is these 2 lenses have surfaces on them to correct the field of view, but in addition to that, they have prism wedges in them. So it's a pair of prisms where, do people here know what an ADC is? It's something everyone should know. Does anyone know? Yeah, okay. So what it is when you point towards the horizon, the atmosphere is dispersing the light. So a star or a galaxy becomes a little spectrum. This thing, it's a pair of prisms that takes that light and puts it back together so that we can observe close to the horizon without actually dispersing, getting all the light into our fibers. So whoever thought of this first, super clever. Okay. This is us delivering those optics to the telescope in 2018. This was before the Ukraine war, so we were able to charter a Ukrainian troop transport plane to do that. And here, this is the assembly this has the 6 lenses in there being assembled onto the telescope. Okay, this is our robotic focal plane. It's hard to see what's going on here, but this is a focal plane that's about this size with 5,000 fiber robots that can take the tips of these fibers and reposition them to the positions of galaxies. And we can reposition these in about a minute, and then we observe for about 15 minutes. And so we do that throughout the night. So on a very good night, actually, we can map about 200,000 galaxies, which is pretty good. So I'll say the biggest survey before DESI was the Sloan Digital Sky Survey. And Sloan Digital Sky Survey was a 1,000,000 galaxy redshift survey. And here I just told you in one night we can actually map 200,000 galaxies. And these are actually fainter galaxies. Okay, there's a figure for you. This is the team that actually assembled that focal plane, or the robots. These are University of Michigan students. So you can see it was a very labor-intensive effort. So over a period of several years, these students assembled all of the parts that went into that focal plane. And I think the figure that I've heard is that focal plane has something like 600,000 parts. Okay, this is just a layout of what the spectrographs look like. We have 10 of these spectrographs. They split the light into 3 different cameras for coverage over the full optical wavelength range. These were built in France. That's why they speak French. And this is one of the last ones being delivered into the telescope. Oh, I love this picture. You just see the rows and rows of cryostats for the detectors. Okay, this was our first light observation. So we pointed at the Triangulum galaxy. It was a nice big galaxy. The reason we did this was when you first start, not everything works. And for example, we didn't know exactly where all the fiber robots were on the focal plane. But it doesn't matter when you're pointed at a galaxy that's a degree across in the sky. You can't miss. So this was our first light observation because we knew we were guaranteed to get 200 observations of this one galaxy, which we did do. Survey started in March 2020, and something was going on in March 2020. I'm trying to remember what was it? Oh yeah. So this wasn't the best timing. So we were just starting to get data March 14th. We were ordered to shut down on March 16th, which, thank goodness we got some data, because there's a huge difference between a little bit of data and 0 data. So it turns out we had a little bit of data, which actually allowed us to make quite a bit of progress up until we went back on the sky later that year. So I'd say it cost us less than 6 months, the COVID pandemic. Then once we were operating for a year, this happened. So this is a forest fire that overburned the entire summit where the telescope is. So this actually shut us down for a couple months again. So this fire, it destroyed power, internet, the road, you name it. But the telescope and the instrument were fine. So we got back operating a couple months later on generator power and hard drives that people would drive up and down the telescope. And then last year we had pirates. So they shut down the observatory. They actually shut down, I think, 3 observatories around the world, including, Gemini was shut down for many months. We actually only shut down for a few days, and then we started operations again without internet. So again, we operated for several months without any connectivity to the mountain. But we already knew how to do that because we had a forest fire the year before, so fine. Okay, so despite plagues, fires, frogs raining down from the sky, we've still made good progress in the survey. So this is a plot of how many galaxies and quasars, or how many millions of them, we've measured redshifts of since the start of the survey. And you can see some of the shutdown periods that I was just referring to. But even still, as of last week, we have 31 million galaxies that we've mapped. And this is a fun exercise. If you take every other redshift survey in the world on every telescope over all of recorded human history and add them up, you get 5.0 million. So this already greatly supersedes all of that. So it's good, it works. Okay, now what does our data look like? This is our most typical observation of a galaxy here. Okay, so this is, which one? It's this galaxy right here, the little fuzz in the image here. This is our spectrum, and what you see here, this is not signal, this is noise. Noise, noise, noise. Looks terrible, right? But if you zoom in a little bit, there's this transition feature. This is singly ionized oxygen. This produces a doublet feature that's very distinctive. So in fact, even though you first look at this data and you say, this is the worst data I've ever seen in my life, we can measure a redshift. So this is the bulk of the galaxies that we're actually observing. If something's bright, we get very good data. So this is a bright quasar, actually at a much higher redshift, but we do have, we are observing every quasar that we can, and for the brighter objects, the data is exquisite. Okay. Another important thing that we've implemented for the survey is a uniformity criterion. So when we observe, we're continually tracking every 15 seconds how bright the sky is, what the seeing is, what the transparency is because of clouds, and we actually tune our exposure time so that this is the plot that the observers see at the telescope. It's a running track where they're counting how much signal to noise we've accumulated on these galaxies as a function of time. And so the way that the survey operates is we'll open the shutter, we'll observe until we hit this threshold, then we close the shutter and move on to the next observation. So at the end of the night here, you see this has gotten slower, so maybe clouds came in, or the seeing got worse. And then at that time, these observations might be 3 times as long as the ones earlier in the night. And then the other thing I point out here is we actually have 2 interleave surveys. So most of the time, we're looking at these faint, distant galaxies. When conditions are worse, we're actually observing bright nearby galaxies, and those are these shorter exposures here. Okay, so the results that we've published so far, they're based on the first year of data, 5.7 million galaxies. These are the different samples that we have. We have a bright galaxy sample, some luminous red galaxies. Most of our objects are these emission line galaxies, and then quasars at higher redshift. And then this is an actual 3D map that David Kirkby has made. So this is a fly-through of that first year of data, placing the galaxies at the proper 3-dimensional location of each galaxy. So this is fun to watch. Okay. Then we move on to analyzing these data. So this is either in configuration space or Fourier space. So this is what the acoustic peak looks like in one of the, actually this is a bin that includes both the luminous red galaxies and the mission line galaxies. These are just the luminous red galaxies in Fourier space. So the acoustic feature in real space and configuration space, this is a single peak. This is the how far the sound wave has traveled. If you take a Fourier transform of that, you get several peaks, which is just the FFT of this one peak. Okay, for this first year analysis, we've divided these samples into 7 different redshift bins. And then this is a measure of what the acoustic scale is. And this plot here is, you can see the BAO feature at each of these redshifts. And then this is a comparison to the straight line here, 1, was our best fit cosmological model prior to DESI. So this is the Planck 2018 cosmology. And then you can see the DESI data actually is pulling this best fit cosmology fit specifically at lower redshifts. So this kind of summarizes the results here. Then you can try to interpret this, and these papers just came out 10 days ago, so there, I think lots of people will be interpreting this in the coming months. but this shows in one of these parameter spaces the constraints from each one of the different samples of galaxies, where you can see that they're all consistent. This isn't particularly different from the figure I was showing before, but this just demonstrates the consistency between the different samples. You can fit for the curvature of the universe, which is measured to be flat and even flatter than you had from any previous data. You can look at your constraints on the Hubble constant, and this is actually looking at the Hubble constant versus the sum of the neutrino masses. And this is getting very interesting because we know neutrinos have mass, and they have a minimum mass somewhere right around here. And you can see that that's actually almost already in tension with these data. It pushes the Hubble constant to be a little bit on the lower end. This particular figure, though, this does include certain priors that I'm not going to go into, but some people, at least anyway, think this is one of the most interesting things that we've measured so far from DESI. Okay, and then the Hubble constant, this is just some of the current results for the Hubble constant, where all the distant measurements from CMB and BAO prefer, I was going to say the correct value of the Hubble constant, I'd say the smaller value of the Hubble constant, so around 68. But then there's more than just this one measurement. There's a whole set of measurements based on local measures of the Hubble constant that prefer larger values. So this is one of the current tensions in cosmology between these more distant measures and local measures of the Hubble constant. Okay, then you can ask if we're consistent with a constant dark energy, so essentially lambda CDM. And if you take just the DESI data with the CMB, this is fairly consistent with lambda CDM. But in fact, when you combine these results with supernova compilations, so this was part of the reason that it took us a few months more to get the DESI data out. So we actually unblinded the data in December. We only published this month because as we were writing these papers, these different compilations of supernova cosmology were being published. And so we took it upon ourselves to analyze the DESI data in conjunction with these different compilations of supernova data. This plot right here, this is looking at a parameterization of dark energy that is a dynamic model for dark energy. So just one of the parameterizations where you allow dark energy to change with time. And lambda CDM would be up here. But depending on exactly which supernova data set you're looking at, this is at some level in tension with the supernova data, at least. So this is potentially hints that there's a time varying W for dark energy.
Did you guys try to do, I don't know, I need to check the paper, but did you do an analysis picking different types of source instead of taking the full survey with all the different types of data? Picking, for example, just luminous red galaxies and CMB to see if you, depends on the type of data you pick?
So I don't think we specifically did that, but that tension, it primarily actually comes from the lower redshift samples from DESI. That's right. So I think it's the case that if you remove, so this is the Lyman alpha Forest data point here at highest redshift. I mean, I don't think these points are driving that fit. I think that's where we are. and I think that's primarily just because you also have the CMB tying you down at high redshift.
And the redshift range of the supernova data is?
Well, it's mostly, it's mostly below redshift of a half, let's say. It does go out to higher redshift, but that's where a lot of the constraining power is. Yeah. And I should say, those are the redshifts where right now the BAO data is not as constraining. So, and in fact, fundamentally, there is a cosmic variance limit to these measurements at low redshift, just because we only have so much volume of the universe to look at the BAO scale. And this is an area where the first year of DESI results actually aren't any better than previous results, just because we've only covered a small fraction of our footprint so far. So in fact, there is in the paper, there are analyses of, well, what if you put in the SDSS BAO constraints at these same redshifts? The story doesn't change very much, but there are those looks at the constraints in the papers.
Sorry.
Mm-hmm.
The previous, that one, no.
Sorry.
This one is also interesting because it looks like the tendencies of the low redshift and the higher redshifts are a bit different.
Well, yeah, there are different projections of this, but it's constraining you. There are different redshifts, so they're constraining you in different ways, which is fundamentally why you want different redshifts in the first place, right? So if you only measure at one redshift, you're not as constraining. Okay, let me move on because I'm worried I'm not going to get to the new stuff at the end here. Okay. So this is the sky map of what was included in these results that I was just showing. This will be the full footprint of DESI. Actually, I just lied. We're actually going to grow this footprint, so DESI will be more than what I'm showing here. Red is the parts of the survey that we've completed. And so you can see for this first year data, it's just this small fraction of the footprint. And then these other parts of the footprint are where we have some coverage, but typically we return to each part of the sky here 5 times to just get the density of galaxies that we're looking at. This is the status of the data right now. So this is our 3-year data that we just finished a week ago. So you can just see it's quite a bit more data. If we were the perfect collaboration, we'd publish this next week. I don't think it'll be next week, but I hope it'll be next year. Okay, so what's next? How much time do I have? It's 3 o'clock. 20 minutes, okay. Okay, but we want time for questions. Okay. We're actually looking at what to do after DESI. And so the project we're designing right now, it's called the Stage 5 Spectroscopic Survey. So this is something that will be on 2 telescopes. One of them, it's this Mael telescope. It's where DESI is running right now. And then there's a twin of this telescope in the southern hemisphere called the Blanco telescope. And so this actually hosts DESI right now. This telescope hosts the Dark Energy camera. What we discovered only in October was that it's actually possible to fit a 6-meter mirror on this telescope. So right now it's a 3.8-meter mirror, but it turns out when this telescope was built in 1972, it's oversized enough that actually that whole telescope mount can fit a 6-meter mirror. It's actually at a different location in that mount. But but you're allowed to do this because the existing mirror in here right now, even though it's only 4 meters, it actually weighs 15 tons. So if you take that out, you have a big mass allowance where you can put in a larger mirror as well. So we have a design here where for each of these telescopes, we replace the primary mirror with a 6-meter mirror. And then the design is actually a Cassegrain design where on the focal plane, instead of 5,000 robots, we have 26,000 robots and lots of spectrographs. Okay, so this is the current design. And what we're looking at doing is continuing these maps for dark energy. So this would be a full sky map. So really to reach this cosmic variance limit out to us as high redshift as we can. So meaning mapping all of the extragalactic sky at lower redshifts. But then primarily mapping the higher redshift sky, so above redshift of 2, and we think we could map about 60 million galaxies. And then there's also a stellar program in here as well. But the key science driver for this project is actually getting at inflation physics. So this is a look at, so again, this is the power spectrum of these galaxies, and then what you'd expect. These are different models for inflation or different neutrino masses or light relic particles, and what the differences would be depending on these different models relative to what the error bars would be with this kind of survey. So this would allow you to easily distinguish between these different models. For dark energy, right now, primarily the data is at this redshift less than 2 range. So this is where we're getting percent level measures of dark energy. And this is a comparison to how much dark energy there is. And so this is we're getting very high confidence measures of dark energy in the more local universe. But above redshift of 2, we haven't really even positively detected the influence of dark energy. So the data just aren't good enough to, we can infer that, oh, there must be dark energy there, but it's not really measured. But this is something you could do with enough galaxies at high redshift. And then finally, there's a third science driver for this program, which is measuring the effects of dark matter on the halo of the Milky Way. So the idea here is to map out of order 100 million stars in the halo of the Milky Way to see influence of clumps of dark matter.
So what are those cubicles?
What's that?
There are cubes flying around.
Cubes flying around.
Those white dots.
Oh, I don't know what those are. I don't know. But we'll find them, whatever they are. I don't know. Those should be obvious, right? They're Borg cubes, that's what they are. Okay, so this is the optical design for these telescopes. I like to show this because it's a very clever design that gets us this large field of view with the large primary mirror, where the lenses here, they're large lenses, but they're all spherical surfaces, which was actually not true for DESI. So the difficulty in producing these large optics, it's difficult to produce optics that are large. It's also difficult to produce optics where they deviate from a spherical shape. And that's just because spheres are easier to measure while you're manufacturing them. But this removes one of the complexities by having all spherical surfaces. And then the mechanical design, this is the clever thing that was discovered that we can fit the 6-meter mirror in. There are some minor modifications that have to be made to the telescope mount, but this actually fits. And this is the thing that has made this whole project much more feasible. So we're not building telescopes, we're just installing instruments. And then for the moment, we're planning on just producing more of the current DESI spectrographs. These are very high throughput spectrographs. In fact, if we were redesigning them today, we wouldn't change anything. So we're just very happy with their performance. The thing we do have to change are the robots. So this project relies on having many more robots. And to do that, we need many more smaller robots. So we've been working on prototyping robots that are about 3 times smaller than the DESI robots. And this is just a graphic of what these look like. Okay, so this is in the future. So this is a project we've been discussing in the high energy physics community in the US for the past several years. It's been recommended by different committees. We've requested a project start date in 2026, but it's a big construction project. It would probably take about 3 years longer to construct than DESI took. So first light would be later in the 2030s. And then let me just close with this plot that shows this is the history of redshift surveys over the past 45 years, okay? And for no good reason, they've been getting larger by a factor of 10 every 10 years. So this is where we are right now, the first DESI data release. I think if we keep building these projects, we can stay on this curve, and you can project out. If you observe the right galaxies, by the year 2043, you could actually map all the linear modes between us and redshift of 4. And then by 2061, so out here, you should be able to map essentially every galaxy in the universe. I'm going to be 94 years old then, and I think that might be when I retire. So I'll stop there. Thank you.
Thank you very much. I do hope that you will retire at maybe 100. So,
can you comment on that, the statistical departure from the lambda CDM you just showed in the, which falls in the 4th quadrant of the plane?
Yes.
Have you, do you have any idea of what it will be, or like Sloan, using the same compilation of CMB and supernovae?
Yeah, I mean, so if you take these results literally and say, this is the universe that we live in, this is the parameterization of dark energy, this is saying that it's a thawing model of dark energy where it's less important today than it would be for lambda CDM. So that's the basic interpretation. But I should say this is very much in conversation right now as far as, you asked me what this means. I'm like, yeah, we're trying to figure that out.
Okay, so you're saying if we were to use Sloan data and then do the same analysis, assuming
with just
WA, and then the statistical departure from lambda CDM would be more or less the same?
No. So do I have that here? No. So Sloan. I mean, the analysis we've done is we've included Sloan at low redshift and then DESI at high redshift. We haven't looked at just SDSS data in this. So I don't know the answer to your question.
So if I read it correctly, for S5, the inflation signal shows up at very large scale.
Mm-hmm.
So this kind of large scale, do you think the cosmic variance or whatever, we only have one universe? Will the data be enough to constrain the signal?
Yeah, no, so it's, so spec S5, it's not getting to the cosmic variance limit yet. So it's, it's a large factor over what we'll have this decade. So if you, we'll be getting to the cosmic variance limit out to redshift of maybe 1 or 1.5 this decade. But there are many more modes at higher redshift, and there are many more modes for 2 reasons. So one of the reasons is there's simply much more universe between, let's say, redshifts of 2 and 10 than there is between 0 and 2. But in addition to that, there are more linear modes per volume of the universe at those redshifts as well, because in the local universe, we've had more gravitational evolution. So structures have gone nonlinear, and they've mixed up the initial conditions on scales less than 10 megaparsecs or something like that. If you go to higher redshift, you can actually go to smaller scales, and you've preserved that information. So in fact, the information content goes up quite a bit at higher redshift. And even with spec S5, it's only a small fraction of what you could measure at those redshifts. It's just technically what we think is achievable for finite dollars. So that's where we are. But it does mean whatever you discover there would be the opportunity to in fact do more.
What role does the telescope in Chile play in the new project?
So the main reason to have 2 telescopes is to get twice as much data. Okay, so that's the short answer. But then the other reason is, it's partly just motivated by these early results from DESI, where we're seeing maybe this departure at lower redshift. But with DESI, we're reaching the cosmic variance limit of what we can do with 1 telescope in the northern hemisphere. So we'd actually like to have full sky coverage to map out as much between redshift of 0 and 2. So that's the other reason to do it. In fact, we've gone through different formulations of what this project could look like. And initially we were looking at, well, maybe we could just build 1 6-meter telescope, put 26,000 robots on that 1 telescope. So that was kind of the initial instrumentation plan. But it's technically super challenging, because then the optics, they're not spherical optics. They're very complicated, large optics. The robots and the spectrographs, that gets challenging to actually, well, we can't even necessarily fit that much instrumentation in the building, so that's another challenge. So there are all these challenges, and then as soon as we said, well, let's just split it in 2, then actually everything becomes easy.
No downsides for observing at 2 sites, maybe when linking the data?
Oh, so the instruments would be the same, so the data would be the same. So we're not concerned about that.
But you mentioned earlier that one of the strengths of the DESI project is that you have all the data measured from one telescope, 1 location. I'm not sure if I understood correctly.
Oh, no. So the big benefit is the data is uniform, but we can still have uniform data from 2 different sites.
Okay, thank you.
So the instrumentation would be identical, and we'd observe the same way. But yeah, other than that, it should be fine. Should be fine.
Okay.
For the slide of the luminous red galaxy, like the distribution of that, very first.
Yeah, I'll get there. There we go.
What I feel that at the left, upper left, upper left part, there's at the boundary there's much redder. Is there any possible bias or?
Yeah, no. So there are a few artifacts in here. And so in fact, what you can pick out by eye is this is getting closer to the Milky Way. And some of these galaxies, they're not really galaxies, but what they are there M stars in the Milky Way superimposed on something else, and then they make it into the sample. Although once we get a redshift, it's not a problem, because then we say, oh, this is a star, it's not a galaxy, and we throw it out. So there's a few % of these objects are stars, and that's also true. We're not observing here, but this is the edge of the Magellanic Clouds. The same thing is happening down here.
So I think inspired by the question. So you mentioned on the talk yesterday that the selection criteria for each one of the galaxies was it like a computer or like because it's like 5.1 million galaxies, right? So I imagine it was not a human-based.
No, we have not looked at all these galaxies. It's a catalog level selection, and for the most part, they're pretty. I don't have them here, but they're pretty simple selections in just brightness and color, and that's it. And the only exception is actually for our highest redshift sample, or high redshift quasars. That's more of a kind of machine learning algorithm, which might concern you a little more. Except we're actually using those as the backlights, the Lyman alpha forest. So if there's some some issues in the selection, it doesn't matter as much for us.
Okay, but what I wanted to know is was there any, let's say, homogeneity and isotropy, in the way you select, like in order to select as isotropic as possible?
Yeah, no, so there are some issues, and I'm showing you these luminous ray galaxies because this is the best looking map. I didn't show you the other ones. Actually, the bright galaxy sample looks just as good. The emission line galaxy sample does not look this good. Those are fainter galaxies, lower signal to noise in the imaging, and we do have issues in the target selection for those galaxies. And then what that looks like is it does imprint some density fluctuations that then imprints on the power spectrum. It does not compromise the BAO results because that feature is so clean and easy, but it does compromise if we're trying to measure large-scale power from that sample. So that's actually a very active area of work in the collaboration right now, is to try to understand exactly what's going on with this angular clustering of the ELG sample.
Okay.
But I didn't show you that, yeah.
But it's in the paper?
It's in the paper? Yeah, it's in the paper, yeah, yeah.
So my question is about the equation of state. So it is parameterized as a linear function of the scaling spectrum. And likely I would expect if you increase the number of free parameters, you will always fit the data better.
Sure.
So I'm wondering, how do we know if this is overfitting or not?
I don't, I don't know, so it might be, it's just, and I'd say we don't have a high confidence measure here, but I'd say this is kind of the first time where we can really try to measure any of these parameterizations. And this particular parameterization, it's not really motivated by any physics model. It's just, you could just think of it as a Taylor expansion of something. That's all it is.
You showed the SPAO's measurements across different redshifts.
Mm-hmm.
Could you quickly comment about what's the dominant factor for the error bars? I would thought it's the number of sources, but then the ones with ELGs, they're not particularly tight compared to the LRGs.
Oh, yeah, no, so they are, it's dominated, there are some details, but it is dominated by just the Poisson statistics of these galaxies right now. The ELG sample is, it's not as complete as the other samples in this first year data. And let me just go to, it's kind of a detail of how we run the survey, which is we do prioritize our fiber assignment for the different target classes. And so we actually assign fibers to the quasars first. And we do that first because the quasars we actually want to observe multiple times because we're measuring the Lyman alpha forest along each line of sight to these quasars. So those are the only objects where we're just repeatedly observing them. And in fact, we do that in such a way that at the location of each quasar in this map, there's kind of a little hole cut out where we're really not measuring other objects. So that was just a choice that we made. We just decided they were valuable enough. We always wanted to observe them. Then the next highest priority are the luminous red galaxies. And so even in this footprint here where we only have some of our data, we actually have pretty good completeness on the luminous red galaxies. But then they've taken priority over the emission line galaxies. So over this footprint, there are very few emission line galaxies. So this is very incomplete. Right. So that's kind of the reason for just those Poisson errors in the first year data. And we made all these decisions knowing that by the end, when we're done, everything's going to be great. But right now we're living in the world where we're not done yet. And okay, it's not exactly what you want the data to look like. And we have these weird patches on the sky that we've observed for different reasons.
So in future results, you expect the error bars for the emission line galaxy to improve much more than the LAG?
That's right.
Okay.
Yeah, that's right. Mm-hmm.
Thanks.
Yeah, and then also the quasars, for quasar clustering, we already have, half of the quasars in the sky just because of what we've covered so far. So they'll actually improve the least in a sense. Yeah.
Final question. So I'm curious for spec S5, the imaging in the cells, will you do it with Rubin? It seems to be the only.
Oh, you're asking me hard questions. Yeah, so I didn't talk about this, but in order to select these high redshift galaxies, I don't think I have anything here. But what we'd like to select them, it's actually not the broadband imaging that Rubin is doing, but we prefer to have narrower pass bands because that can more efficiently find the redshift greater than 2 galaxies. We're starting to do such a survey, as you know, for an extension of DESI using the Dark Energy camera, but just over a smaller footprint of the sky. For Spec S5, what we'd like is much, much more imaging in these different pass bands, which no one is planning to do right now. So the best way to do this would be to take Rubin Observatory, take their filters out, and put in some good filters, and then observe. It would only be about a year of observing with Rubin with a different set of filters.
But they will run from 2026 to 10 years.
We need them to start soon. Yeah, that's right. Yeah, yeah.
Okay, so before closing, I just remember that after Schlegel, Finkbeiner, and Davis' paper was published, Schlegel decided that he hated dust. He didn't want to deal with dust anymore. While Finkbeiner said, thanks, dust is so interesting. He wanted to devote the rest of his life to dust. And I suppose you want to get rid of dust. And I think you will figure out a clever way to do that. too. So let's hope David will continue his endeavor in the discussing dust business.
That's a curse.
Someone here did that for you, so he was the referee.
Okay, so David will be here until tomorrow, and on Friday he will head to Hsinchu to Tsinghua. While he has a pretty packed schedule, feel free to talk to him. His office is 1324. Let's thank him again.